Good day. For those of you who do not know us, we're the instructional staff for ECE 150. Professors Hiren Patel and Verna Dietl and Douglas Harder. In this topic, we're going to look at while loops. So, in this topic, we're going to see how you can implement a while loop in C++. We will show implementations of while loops that play a guessing game with the user, find all the prime factors of a given integer, and find an implementation of the Collatz conjecture. We will learn how to convert a description of a looping algorithm into one that you can program in C++. Specifically, we're going to write a program that calculates the greatest common divisor of two integers. Finally, we will observe that all for loops can be written as while loops. Now, previously we saw a for loop. A for loop is a special case of a repetition statement. Specifically, the loop body of a for loop is executed a fixed number of times based on the initial value of a loop variable, which itself is a local variable, the scope of which, in this case, is restricted to the for loop, a condition on that loop variable, and an update to the loop variable that is executed each time after the loop body is executed. Now, one thing that's nice about a for loop is at compile time, you can very often determine how often the loop body will be executed. In this case, we don't know, but we know that it's n. So once we know what n is, we know how often this loop body will be executed. Now, there are some cases, however, where we do not know at compile time how often a loop may be executed, and we may never be able to tell at compile time. So a for loop may not be the best idea. An alternative approach in programming is called a while loop. A while loop only has a condition and a loop body. The loop body is executed as long as the condition is true. So here's the syntax. We have the keyword while, and the Boolean valued condition appears between parentheses. Following this, the loop body appears between braces. And when execution gets to a while loop, the condition is checked. If the condition is true, the loop body is executed. Once the loop body is executed, the condition will be checked again. If it is still true, we will execute the loop body again, and so on and so forth, as long as the condition evaluates to true. As soon as the Boolean valued condition evaluates to false, then we continue executing after the while loop. Now, here's a very common loop in engineering, and it is called an infinite loop for very good reason. Well, true is always going to be true, so this loop body will be continually executed forever. Think of it this way. Suppose you have a toy that a child is playing with, and that toy is waiting for the child to do something and then react. That toy is simply going to continue seeing if the child has done something forever until either the battery runs out or the toy is turned off. However, there is no reason to assume that we will only have to check 10,375,821 times before we stop checking what the child does. We can already use the for loop in this example where we ask the user to enter a positive integer. So we have a local variable n that is declared outside the loop. Now we have a while loop that will be infinitely running. So this is an infinite loop. We will ask the user, enter a positive integer. We then get that integer from console input, and then we check. If n is greater than 0, that is, it's positive, then we break. Just like a for loop, a break statement will also exit a while loop. So in this case, we can continually check until the user has entered a positive integer. And unlike a human who might be getting a little bored after having asked you 589 times for a positive integer, the computer will just happily ask you one more time. Now, here's an alternative approach where first we ask for an integer and we query the console input for that value the user entered. Now we have a condition while n is less than or equal to 0. Now, the while loop does not start executing until console input has assigned n a value inputted by the user. So if the user inputs a value 7, then 7 less than or equal to 0 immediately evaluates to false, and so this loop actually never runs. However, if the user was to enter -3, -3 is less than or equal to 0, and now we execute the loop body. And in this loop body, we once again make a statement, enter a positive integer. However, we give an additional hint that this means that the integer should be greater than 0. We then query console input to get the next value of n that is entered by the user. Now, suppose we want to create a guessing game. We're going to get player A to enter a number to be guessed, and then player B will continue to guess that number until player B has guessed correctly. Of course, we're going to put this game up on Google Apps, and we're going to make all 10 cents off of it. That probably coming from one of your relatives. Put it another way, that second statement about player B essentially says, inside an infinite loop, query player B for a guess. If that guess is correct, we will break out of this loop. All right, let's see how this works. So here we have our initial setup of our program, and we're going to use an infinite loop. Now, first of all, we're going to have a local variable, secret number, and we will ask player A to enter a secret number. We then query console input and store that value in that local variable. Now we have an infinite loop. We will ask player B to enter guess, and we will store that guess in a variable that is local to the body of this loop, because we don't need this guess outside the loop. So we will query console input and get that value. Now, if the guessed number is equal to the secret number, we will let the user know, you guessed the secret number. And then we'll issue a break. The break will exit out of this infinite loop, after which, of course, this program will terminate. However, if the user did not guess the secret number, we will just simply inform the user that they had an incorrect guess. At this point, the body of the while loop has finished executing, and so now we check if the condition is true. Well, yeah, true is always true, so now we will re-execute the body again until the user does actually guess the number or terminates the program. Control C. Let's refine this guessing game to one that you've already seen in, if not elementary, certainly in secondary school. Player A will now enter a number between a fixed range. Player B will continue to guess this number. If the guess is correct, the game is over. If the guess is greater than the hidden number, we will tell the player that the guess is too high. Otherwise, we will tell the player that the guess is too low. Put another way, in an infinite loop, we will query player B for a guess. If that guess is correct, we will break out of the loop. Otherwise, we will tell the player if the guess was too high or too low. Here we have an implementation of this game. We query player A for a secret number, and we store that number in a local variable secret number. Now, because we want this game to be fair, we want to make sure that the number that was entered by player A is indeed on the range from 1 to 100. So we now have a while loop. So while the secret number is less than 1 or greater than 100, we will execute the body of this loop, which once again asks for player A to enter a secret number from 1 to 100. If the secret number was -5, the first condition would be true, and therefore we would execute the body of this loop. If the secret number was 107, the second condition would be true, and again, we would execute the body of the loop. If the secret number was 51, then the first condition, or the first comparison, is false, and the second comparison is also false. False or false is once again false, and so this loop would terminate execution and we'd carry on running with the next statement. Now, the condition can be different and still perform the same operation. In this case, rather than using the previous condition, we have not with two conditions joined with and. So what does this condition say? Well, suppose the secret number was -5. -5 greater than or equal to 1 is false, and false and anything is still false. So not false would be true, and therefore the body of this loop would be executed. If, however, the secret number was 50, then secret number greater than or equal to 1 is true, and secret number less than or equal to 100 is also true. True and true is true, and not true, therefore, is false. And so if the secret number was 50, this loop would not be executed. And of course, you can try this again if you had a number such as 123. Now, we're not going to have that much of a different issue here as before. We just query player B to enter a guess from 1 to 100, and we're not even going to bother checking because it's only going to disadvantage player B if player B guesses a number that's outside that range. So we check. Is the guessed number equal to the secret number? If so, we will let the user know and break out of this infinite loop, which will then end the program. Now, if the user did not guess the secret number, we will check. If the guessed number is less than the secret number, we will let the user know, too low, guess again. The complementary alternative body of this cascading conditional statement is when the guessed number is greater than the secret number, in which case we will let the user know, your guess was too high, try again. Now, suppose we want to print all the prime factors of a given integer. For example, 123 is equal to 3 times 41, 124 is 2 times 2 times 31, and 125 is 5 times 5 times 5. Now, how would we find the prime factors of 2666? Well, we notice that 2666 is divisible by 2, it's even, and so we know that the prime factors are 2 and whatever the prime factors are of 1333. Now, if you don't know what that is, that's okay. It's actually 31 times 42, but it might take you a while to get there. But again, this looks like an interesting strategy. So start with a number and check if it's divisible by a small prime factor. If it is, divide that, record that we were successful in dividing the number by that prime factor, print that prime factor to the screen, and divide the number by that prime factor. So, for example, 124, we see that's divisible by 2. 124 divided by 2 is 62. 62 is divisible by 2, so we'll print 2 again. 62 divided by 2 is 31. Ultimately, we determine that 31 is indeed a prime number, and therefore we would be finished. We would just print 31. So in this case, we're going to query the user for an integer. We're not going to check if it's positive. We're assuming the user would like an answer, so we're not going to worry about error checking right now. Of course, if you're writing this in an application, you may indeed want to check this. However, we're going to query the user for a value, and we will store that in the local variable n. Next, we have a possible factor. We're going to start by trying to divide n by 2. And as long as n is divisible by 2, then we know that 2 is a factor of n. So here's our loop. While n is greater than 1, we will check, is n divisible by the positive factor? That is the remainder when n is divided by the possible factor equal to 0? If so, then we will print the possible factor to the screen, followed by a comma. We will then also divide n by that possible factor. So once again, initially the possible factor is 2. Alright, so if n was 124, then 124 modulo 2 is equal to 0. So we would print out a 2 and divide 124 by 2, which is now 62. 62, when divided by 2, has a remainder of 0. So once again, it's divisible. Therefore, we will print 2 again and divide 62 by 2, leaving us with n being assigned the value 31. Ultimately, we'll determine that 31 is another factor. Now, once we've checked how often the number was divisible by 2, ideally we'd like to go up to the next prime number. 3, then 5, then 7, then 11. But is it all that bad if we just increment possible factor by 1? Not really, because we've already divided the number by, for example, every single time it could be divisible by 2. If we've already factored out the powers of 2, then it's impossible, for example, for the result to be divisible by, say, 4. So the condition that n has a remainder when divided by possible factor equal to 0, that will only be true if the possible factor is prime. Now, if you want to be a little bit more intelligent, there are techniques to find prime numbers. However, this works for now. All right, next, let's look at something called the Collatz conjecture. This says that if you start with any positive integer n and repeat the following process, if n is even, divide it by 2. Otherwise, n is odd, and therefore multiply it by 3 and add 1. If n is ever equal to 1, then the sequence carries on forever. 1 times 3 plus 1 is 4. 4 is even, divided by 2, we get 2. 2 is even, we divide that by 2, we get 1. 1 is odd, therefore we multiply it by 3 and add 1, bringing us back to 4. The Collatz conjecture says that regardless of your initial integer value of n, this sequence always ultimately gets back to 1. Here are some examples of sequences generated by this algorithm. For example, 9 times 3 plus 1 is 28, which is odd, so we divide by 2, giving 14. We divide that by 2 to give 7. 7 is odd. 3 times 7 plus 1 is 22, which divided by 2 is 11, which is once again odd. Times 3 plus 1 is 34, which is again even. Divide that by 2 to give 17, which is odd. So we multiply it by 3, add 1, so on and so forth. And yet ultimately we get back to 1. Here are some longer examples. If you start with 27, this goes on for 112 iterations before we get back to 1. Starting with 171, this requires 125 iterations before we get back to 1. Notice, of course, as soon as you get to the same value, afterwards, the sequence of numbers is once again the same. So let's implement this as a program. We query the user for a positive integer. Now what we're going to do is we're going to check as long as n is not equal to 1, and as soon as n is equal to 1, we will just print out the number 1 followed by an end-of-line character. Inside the loop, however, we will print the value of n followed by a comma, and then we will check. If n is divisible by 2, that is, the remainder when n is divided by 2 is 0, so if n is even, we will divide n by 2. Otherwise, we will assign n the value of 3 times n plus 1. This will loop until n ultimately does equal 1. Notice here I was very careful in the sense that I do not have a comma after that final 1. It just looks a little bit nicer. Now, suppose you're given an algorithm and you'd like to implement that in a program where in this algorithm you have to repeat a number of steps. How do you make the transition from what you probably did on paper to writing that algorithm as a program? Our recommendation: do the algorithm on paper in full. Examine the steps you took and then determine what steps were repeated, what conditions caused you to stop repeating those steps, and what local variables could you use. All right, let's do this with something that you're familiar with: the greatest common divisor. In secondary school, you saw an algorithm and hopefully learned an algorithm to calculate the greatest common divisor of two numbers. For example, suppose you're asked to find the GCD of 8008 and 8085. What you did is you noted that 8085 was greater than 8008. Great. Now, the remainder when 8085 is divided by 8008 is 77. What you then did was you then found the remainder of 8008 divided by 77, which happens to equal 0. Well, in that case, you know that the GCD of these two numbers is 77. Okay, that went a little quick. Let's try this again with slightly larger numbers. What's the GCD of these two numbers? Well, we first determine that the first one is indeed larger than the second, and the larger number divided by the smaller number has a remainder of 39,490. We then find the remainder of what used to be the smaller number when that is divided by the remainder we found. Well, the remainder of 85,800 when divided by 39,490 is now 6,820. The remainder when 39,490 is divided by 6,820 is 5,390. The remainder when 6,820 is divided by 5,390 is 1,430. The remainder when you divide 5,390 by 1,430 is 1,100. The remainder when you divide 1,430 by 1,100 is 330. The remainder when you divide 1,100 by 330 is 110. And the remainder when you divided 310 by 330 by 110, that has a remainder of 0. As soon as you have the remainder equaling 0, the smaller number is the GCD. So the GCD of the original two numbers is 110. However, how would you do this on paper? Well, if you did this on paper, you'd start by writing out the two numbers in columns. You then calculate the remainder. You then copy the two numbers over and calculate their remainder. Copy the two numbers over, calculate the remainder. Copy the second and third numbers over, remainder. Copy them over, calculate the remainder. Copy the second and third to the left and calculate the remainder. Copy the second and third over and calculate the remainder. Copy the second and third over, calculate the remainder. The remainder is 0, and therefore the GCD is the middle number. All right, straightforward enough. So what we can do now is we can give the first two columns identifiers, or what we will declare them as local variables to which these values will be assigned. The third column is n modulo n. All right, so what did we do here over and over again? Well, we kept on calculating as long as the remainder was not equal to 0. If the remainder was not equal to 0, we calculated the remainder and stored it in a local variable that's temporary only to this loop. We then set m to the value of n. So we assigned m the value of n. We then assigned n the value of the local variable rem, which we were temporarily using to store the remainder. That's it. That is the entire GCD algorithm. Once this loop finishes, the GCD is the integer n, whatever n ends up being assigned to after this loop is executed. All right, so here's our program. We're going to have two local variables, m and n. We will query the user to enter a first integer, and we will get that first integer assigned to m through console input. Now, the greatest common divisor of two numbers is the same whether or not the number is positive, or either number is positive or negative. For our algorithm to work, we expect the integers to be positive. So if we want to find the GCD of -6 and -3, well, we're just going to calculate the GCD of 6 and 3. So if m is less than 0, we will assign m the value of -m. Same thing for the second integer. We'll query for it, and then we will check. If it's less than 0, we will assign n the value of -n. All right, the first thing we have to do is make sure that m is assigned the larger of the two integers passed by the user. So we're going to check. If m is smaller than n, and fortunately both m and n are positive now, so that's not an issue, we will then declare a local variable temp, which is initialized with the current value of m. We will then assign to m the value stored in the local variable n, and then we will assign to n the value stored in that temporary variable. So after this if statement is executed, the values of m and n will be swapped, so therefore m must be greater than or equal to n. Next, we run our GCD algorithm. And that is the algorithm we saw previously. As soon as this algorithm is finished, the GCD is n. And our program is finished. Now, did you catch the mistake in the print statement? The GCD of m and n is n. Well, originally the user did input two integers m and n, but we've modified them throughout our algorithm. So those two local variables no longer hold the original values. So how could we print the original values? Well, one solution may be to store m and n in two other local variables. However, we're going to sort of cheat. Now, rather than seeing just one implementation of an algorithm that calculates the GCD, here's another. If we take a look at this code, before the while loop, I calculate the remainder. So now we have m, n, and the remainder assigned to three separate variables, m, n, and rem. Now the while loop is as follows. While the remainder is not equal to 0, I update each of the three values. M is assigned the value of n is assigned the value of the remainder, and now we recalculate the remainder once again for the next iteration. As soon as the remainder is equal to 0, this while loop will terminate. All right, so there's two different approaches, and there are many, many more approaches. Now, testing is something that's very important. If you give as input two prime numbers, the GCD should be 1. And here are two examples of prime numbers, and yes, the GCD is calculated to be equal to 1. In this second example, the second integer is an integer multiple of the first one, in which case, of course, the GCD should be the smaller of the two numbers, and yes, we see that happened. Notice that in both of these cases, I included the larger number second to test to make sure that the first and second entries are swapped appropriately. Now, if two numbers are relatively prime, but still quite composite, meaning that they have many prime factors, but they do not share any of those prime factors, the GCD should still be 1. And so here in the first number we have, I believe it's 2 times 5 times 11 times 17, maybe times 23. Anyway, and the second one is a multiple of the other small prime numbers. And yes, we see here that the GCD is equal to 1. Actually, we could use the previous program we just implemented a few screens back to find all the prime factors, if you wanted. In this case, both of these numbers share a significant number of prime factors, and the GCD is indeed what we expect it to be for these two numbers. The other thing we should test is having negative numbers. So what I'm going to do is I'm going to take a test that we already have, and I'm just going to negate the first one, then the second, then both, and we should get the same answer. And so yes, in all three cases, the output is as expected. Now how about if one of the integers is 0? If one of the integers is 0, the GCD should be the other number. So if we enter the first integer being 0, the second number being 512, the greatest common divisor of both those two numbers is 521, because 521 divides both 521, but it also divides 0. Problem: floating point exception core dumped. I don't remember typing that to the output. No, what's happened here is we've actually had a floating point exception which then terminated the program. The issue is, just like if you divide by 0, that causes a program to terminate, at least for integer division, the same thing happens if you try to calculate the remainder when dividing by 0. This causes a floating point exception and causes the program to terminate. This is not good if you need the program to actually calculate something significant. And in fact, one satellite you'll find about later, it actually had something like 2,000 floating point exceptions, the last of which finally caused the satellite to expend most of its fuel spinning in circles. Wasn't the greatest day in the world. Anyway, so one thing our code did not account for was if one of the two arguments was 0. So if one of the two arguments is 0, then the GCD is the other number. We'll fix this as follows. Once we've made sure that m is the largest of the two, it could still be 0, then we check. If n itself is 0, I'm going to print out to the screen the GCD is m, the other number. Now notice what I'm doing here. After. Immediately after my print statement, I'm saying return 0. Now you'll remember that at the end of the function we return 0, but it's also possible to end this program early by issuing a return 0, and we will see more about that later. One important thing you have to remember is that every single for loop can be trivially written as a while loop. So the following two loops are essentially identical. Here I have a for loop that calculates the sum of all of the integers from 0 to n minus 1. This is the corresponding loop using a while loop. As you can see, there is a loop variable which is initialized a value of 0. The loop continues to run as long as the condition k less than n is true, and if the condition is true, then the loop body is executed. Once the loop body has been executed, the update statement will be executed, and then we will test the condition again. The for loop is easier to understand visually because all of the information about the loop is in a single line. You never need a for loop, but it's more convenient and easier for the reader to understand the intention of the programmer. The reason I say they are essentially identical is because the loop variable k in the for loop is local only to the loop. However, in the second example of the while loop, the loop variable k had to be declared outside the while loop, and so the loop variable k is still accessible after the while loop is complete. So that's why I simply say they are essentially identical, not exactly identical, but for all intents and purposes, these two loops are the same. So, following this topic, you now understand how to implement a while loop in C++. You have seen how to implement various algorithms requiring looping statements, including a couple games where you were trying to guess an integer. We also found all the prime factors of a given integer, and we implemented the Collatz conjecture. We also then described how we can convert a description of an algorithm that loops into one that actually is implemented as a program. Specifically, we looked at the greatest common divisor algorithm, and we saw that while it might be rather annoying to implement in the real world, it actually once we made sure that the integers were in the correct order, it was restricted to a small while loop that only had 3 statements in the body, which is actually rather elegant. We also understand that all loops, for loops, can be written as if they were while loops, although there are benefits to using a for loop if that is your intention. And at the end, we looked and saw quickly how you can terminate a program that's gotten into an infinite loop.